Let me now introduce you to the concept of Airmass, the Airmass coefficient. This is important figure of merit which gives you an idea of the path length through which the spectral irradiance or the insolation vector passes through the Earth's atmosphere before it reaches the flat plate collector placed on the surface of the Earth at a given locality. So this path length will differ from time of the day, time of the year, and also the place, geography, and based on this, the amount of attenuation will also vary. Though this does not give any idea on the climatic condition or does not even use the climatic condition, but it uses the physical geometrical properties, that is the zenith angle property, to give you an idea of the amount of atmospheric length that the sun rays or the irradiation vector has to pass through before it reaches the collector, and the amount of absorption or the attenuation that may happen. So this air mass coefficient is an important coefficient which is used as a parameter for comparison. It is a benchmark parameter which is used to compare various panels under standard air masses. It is also used to compare the spectral data from the spectral irradiance data of various measurements of various peoples done at some standard air masses. Let us now see how we calculate the air mass coefficient and also how it is visualized. Now let us consider this picture. This picture here, as I am showing on this cursor, which is tracing this circle, is the surface of the Earth, and this second concentric circle which I am now tracing is the boundary of the atmosphere, outer atmosphere. Beyond that is free space, and in between the gray shaded area is the atmosphere. Now there is this red line drawn from the center of the Earth, passing through the point of interest, which is the locality, passing through straight up, and this is actually the zenith axis. And there is another line from the center of the sun right up down to the point of interest, which is the locality, and this actually is the insolation line. So we know these terms, and using this, let us try to define what is the air mass coefficient, and let us see if we can calculate the air mass for a given place. Now this is the zenith axis Z, and this white colored circle is the Earth, and this shaded area is the atmosphere, and this angle is phi, the latitude, and this angle is the zenith angle theta Z. Now let us try to define two distances, lengths. One length is here, just along the movement of this cursor here, just along the zenith axis from the surface of the Earth at sea level, along the zenith axis up to the outer atmosphere. Now that is the reference length, and we shall denote it by unity, that is the reference. Now the other length is this length, which is along the insolation line, starting from that locality at sea level and goes through the atmosphere in this path, cuts the outer atmosphere at this point and goes on towards the center of the sun. Now this length is the longer length, and is basically the hypotenuse, and this we shall define it as L, lowercase l. Now let us write the statement for the air mass coefficient. Now let me write that statement first. Air mass coefficient defines the direct optical path length of the insolation through the atmosphere. What it basically means is that the air mass coefficient defines the direct optical path length. This is the direct optical path length of the insolation. The insolation, this is the insolation line, the insolation vector is along this line. What is this direct optical path length up to the collector? Now that is actually defined by the air mass coefficient. Now this is always referred, the constraint for this statement is always with reference to this zenith axis length. So this is expressed relative to the zenith path length, which is normal to the horizon plane located at sea level. This is the definition. Now knowing this, now we can say the air mass. This is the symbol for air mass and the coefficient L, AML. This is how the air mass coefficient is written. So where L is actually obtained from the trigonometry, L is actually the hypotenuse. This is one of the sides of the right angle triangle. Theta z is the angle. So cos theta z is 1 by L, or L is 1 by cos theta z, which is nothing but secant theta z. Now air mass 1, let's say air mass 1 means L is equal to 1, occurs when theta z is 0 degrees. What it means is that theta z is 0 degrees, is insolation line is in line with the zenith axis, which means it is directly overhead. During that time, the insolation vector passes through the minimum distance through the atmosphere, and that is the reference distance. But normally that is not what happens. The air mass length is much more, the path length is much more than the minimum distance, and the standard is not AM1, the standard is AM 1.5, which is around 48.2 degrees. We will come to that later. Now AM2 occurs when theta z is 60 degrees. So when theta z is 60 degrees, cos theta z is 0.5, L is 2, and that is why you call it as AM2. So the moment you see this symbol, this air mass coefficient symbol like this, you know that the zenith angle is 60 degrees. So these AM coefficients are pretty popular and used as benchmarks in many places. In fact, even in the PV photovoltaic panel data sheets, you will see the air mass parameter coming into the picture, because they use it as a benchmark in comparing the PV panels. And also it is used as a benchmark for the spectral studies, especially when comparing the spectral irradiance data obtained from various locations. What is AM0? AM0 is generally used for path lengths in free space. That is when there is no atmosphere. So for all the extraterrestrial insolation vectors where there is no atmospheric attenuation or absorption, AM0 is used. AM1 we know is along the zenith, when the insolation is along the zenith axis. AM 1.1 implies theta z zenith angle is 25 degrees. AM 1.5 implies zenith angle theta 48.2 degrees, the zenith angle, and AM 2 implies theta z is equal to 60 degrees, which we saw, and so on and so forth. But what is important to note is standard. What is the standard? This AM 1.5, where theta z is equal to 48.2 degrees, is the standard for air mass, and that is the standard benchmark which is used for comparison of the PV panels. Consider the following insolation line they have drawn. This is the sun position, and also another sun position like this. You see, these are positions for the northern hemisphere. This sun position would be winter for this particular locality, which is situated on the northern hemisphere. So the sun is moving like this from Tropic of Cancer down to Tropic of Capricorn and then up again. So as the sun is moving, the path lengths are varying, which means that it travels through the atmosphere with different path lengths, and therefore you will have different attenuation factors over the year. So you can say that is the path length at some value of theta z here. Then there is this path length at different time in the year, and this is the path length when it is at probably close to the Tropic of Capricorn or still near abouts. So this angle, let us say, if it is 48.2 degrees, 48.2 degrees zenith angle is considered as the air mass standard, as this is applicable for most of the land masses which are occurring at the temperate zones in the northern latitudes and the southern latitudes. One more point before we close this topic of air mass is this air mass. Now I'll call it as L star. What it basically means is that most of the air mass by definition is for the path lengths up to the sea level. However, on the surface of the earth, the heights of the places are varying. There are some places at sea level and there are some places on top of the mountains. And how do you take care of the height of the place above sea level? Because once you give a particular latitude, it is mostly in terms of the zenith angle where the height of that particular place is not reflected. However, the path length will vary depending upon the height of the place. So one measure that is normally used is L star, where L star is a modified value of L, and it is given by P by P naught into L, where P is the pressure at the place which is at a raised altitude, let us say, and P naught is the pressure at sea level. So if the place is at sea level, then P and P naught will be same, and therefore L star will be L, and the usual factor coefficient holds good. In case the place is at a height above sea level and the pressure is lesser, and therefore this factor is a value less than 1, and therefore L star will be less than L, and therefore the optical path length of the place at a height will be less than that of the place which is at sea level. So this correction factor can be taken and is normally used to address places which are above the mean sea level.